So I started this teaser section about infinite graphs with an appetizer. I'm going to finish it off with drinks after dinner. So what I'm going to show you now is not going to be full of proofs, but full of exciting stuff. And it's very much an advertisement for infinite graphs as we treat them here at Hamburg. It all started with the need for infinite cycles in infinite graph theory. If we wanted to generalize known theorems, important known theorems, standard known theorems about finite graphs to infinite graphs. Now, we have not treated that many or had that many theorems involving cycles yet. We're going to have a whole chapter on Hamilton cycles. So a Hamilton cycle in a given graph is one that uses every vertex. Right? And obviously you can't have that in an infinite graph unless you have something like an infinite cycle. There are other motivations as well. They have to do with what is known as the cycle space of a graph, which I haven't defined, so I won't go into that. But there was a need for infinite cycles. Now, algebraists would say, oh yeah, easy. A cycle is a two-regular graph. So let's just take the infinite two-regular graph. Now, the little boy in me would say, oh, no, that's not round. That's not a cycle, that's not round. A cycle has to be round. Okay, there are more subtle counter-arguments against using that, but it is true that people have tried, or did try for decades, to prove interesting theorems about that sort of infinite cycle, and including Hamiltonicity results, and not much came of it. I mean, a lot of work was expended, especially by Nash Williams, one of the champions of infinite graph theory in England, but nothing particularly interesting came out of that. So, not that. That's not going to be a cycle. A cycle's got to be round. Okay, in order to have something round that looks like a cycle, we need ends. Ends for a graph are things like points at infinity. So let me just give you examples first, and then give a formal definition. So here's the two-way infinite ladder, and that has two ends, one on the left and one on the right. Points at infinity, whatever that means. All right? That's the Z by Z grid. So this is the double ladder. It's not quite clear what to do with that. Is there a point at infinity? And where is infinity? Well, if you think of it as being as sort of occupying the entire plane, then you have seen that the plane sort of can be wrapped round to a sphere, and then there's one point missing, and that one point that is missing is the point at infinity for our informal notion. So this has two ends, this has one end, and then there's the binary tree T2, which we had seen before, and that has how many ends? Two to the aleph not many ends. Right, one for every left-right sequence, starting here. Right, you can't prove that, or we can't prove that yet because I haven't defined ends. So here's the definition. It's an equivalent class of rays. And rays are one-way infinite paths. Where R and R prime two rays are equivalent if we can't separate them by a finite set of vertices. If and only if there's no finite set of vertices that separates R from R prime in the graph. All right? So whenever we delete a finite set of vertices, there's going to be a path from what is left of one to what is left of the other. Now, maybe this finite set of vertices hits some vertices in R, and maybe it hits some vertices in R prime. And then for good measure, we could add all the vertices before those in R and R prime also to our finite set. It still won't separate. So the tails, after those vertices that we deleted, they are still not separated by this finite set. So for every finite set, there exists a component that contains tails of R and R prime. Right? So you can still get from R to R prime after deleting this finite set. That's the definition of when R and R prime are equivalent. And an end is an equivalence class. So all the rays that go eventually right are equivalent because where are two rays that go eventually right? For example, the bottom ray and the top ray. But also this ray that does that wheels through a little bit. They're all equivalent because if you delete finitely many vertices, then they're still adjacent in their tails. But if you take one that goes eventually right and one that goes eventually left, so maybe goes right for a long time and then left, then there is a finite set that separates those two. Okay, so this has two ends. The grid only has one. If you delete a finite set of vertices, then any ray is in the grid can still be linked in the rest to any other ray, because each ray hits this finite set of vertices only finitely many times, and then after that, they can still be joined because this finite set is contained in some ball here, some little disk in that grid. And that argument, by the way, also shows that this component here is uniquely identified by the end, right? Every vertex, every ray equivalent to this particular R must eventually sit in that component of G minus S. Yeah, because if it went in there finitely often, but didn't have a tail in there, it can't visit infinitely many times without having a tail in there because it can pass through S only finitely often. So if it doesn't have a tail in there, it will eventually be disjoint from this, so it will have a tail disjoint from this. and then delete everything before that tail added to S, and that will be a finite separator between that ray and R. So this component here for every S, the component of G minus S, where the rays that are in a given equivalence class have their tails, is uniquely defined. Okay, so these are N's, and here too, if you take two rays from the root that are different, they will part ways at some point, and then they will never meet again. So this finite common segment will separate them. Okay, so that's N's. Now, on to something round. So this graph here has three ends. Okay, here's an attempted definition of infinite cycle. It's not going to be the final definition. Let's attempt to say, or to call this an infinite cycle. So what's this? This is a union of double rays, disjoint double rays, whose tails are equivalent as indicated by these ends. So we have a sequence ray, end, ray, end, ray, end. Like this. We have something like a C3, like a cycle of length 3, except that these are ends rather than vertices, and these are double rays between them rather than edges. Or we have something like that. So it might be tempting, and I did try that 20 years ago, to define infinite cycles as precisely that. So alternating sequences, finite alternating sequences between double rays and ends with incidences just as you have them between edges and vertices in a cycle. So this double ray here must have one tail, an element of that end, and the other ray, an element of that end, right? Just like edges are incident with their end vertices. Yeah, so these will indeed turn out to be infinite cycles, but they're not all. So it's pretty easy to see that they shouldn't be all, because if it makes sense to take our cue from a finite cycle and come up with this and call it an infinite cycle, what did we do? We took a finite cycle, replaced vertices with ends and edges with double rays properly incident. Yeah, but if we can do it once, why not again? So this has lots of, let me do it in a new picture. This has lots of edges up there. So take these vertices and these edges and do to these vertices and edges what we did to these vertices and edges when we went from here to there. All right, so what's that? Well, replace every vertex with an end and every edge with a double ray incident with this end. So these vertices get sort of lifted to vertices somewhere at infinity, and whenever two of them used to be adjacent, right, form an edge down here, we get between these ends a double ray. So there's a double ray between these two vertices, and there's a double ray between those two vertices, and so on. Oops. Right, lots of double rays like this. And I drew them like this. I didn't use the same ray, but that doesn't matter. So they both have to have this end be an element of that end or converge to that end informally. So we just put a ladder there. Right, and then, okay, so we need to hook this onto here. To complete the picture. Right, so if that counts as a proper infinite cycle by this argument that we just take the analog of a 3-cycle and do the replacements, vertices to ends and edges to double rays, if that analog, taking that analog is justified, then why should it not be justified here? But if it is justified here, ooh, we can do it again. So rather than having these edges here, we have little things here. Okay, and for the others maybe as well, or maybe for some and not for all of them. And then we can do it again there. And then we can have funny examples where we don't do it 17 times, but we leave those intact, but do it once here, and then only 3 times there, and then only 4 times in the others, and so on. We get sort of diagonal constructions. That didn't lead to a lot. I tried. And so we tried to define some combinatorial notion of taking these limits transfinitely, and it just didn't work. Then there was a miracle rescue. A miracle happened, and the miracle is called topology. Make G plus n's into a topological space, which we shall call mod G. So G is now locally finite. To make things neater. It's also possible to do that for arbitrary infinite graphs, but the theory is not nearly as nice. So for locally finite graphs G, it's completely clean and nice. How is that defined? Well, G itself is a topological space. Yeah, so it's a simplicial complex, and I can give you the open neighborhoods on foot. So open neighborhoods if you have a vertex, if you have an inner point of an edge, think of that edge as a copy of 0,1, of the real interval 0,1, a homomorphic copy with this the image of 0 and this the image of 1, and then take any inner point of that, take an open interval around it. Declare that as open. For vertices, do the same thing. there are only finitely many edges at that vertex. So take these open half intervals in your complex. And for n's, take any finite set, take any component of the rest, and I have to draw this slightly differently. Give ourselves more space. So take any component here, C, and then there are some edges from C to S, and declare as open the entire set C, so all the vertices in there, all the points on edges in there, plus some choice of half edges there, open half edges there, and all the n's that live in this component. And I told you earlier that that's well defined, right? So for every end, all its rays will eventually end up in one of these finitely many components. S is finite, the graph is locally finite, there are only finitely many components, and every ray can cross S only finitely often, and after that, it disappears into one of these components, and equivalent rays must disappear into the same component. Therefore, an end lives uniquely in one component. So once more, a basic open set is the entire component C, all the vertices and all the edges, union of all the edges, and the set of vertices in there, and the set of all n's living in that component, and these open things. Okay, so that's a very simple, standard topological space. And it turns out that if we define a cycle as a circle in this space, and a circle means something homeomorphic to the unit circle in the complex plane, then this is a circle, this yellow thing, because one can easily check that what the definition implies, that rays converge to the end of which they're an element. Right? For every finite set, no matter how large a ray has a tail in the same component of the graph minus that finite set in which its end lies. So in this sense, rays converge to their ends, and this is indeed a circle. So is that. No matter how often you play this silly game, it's always still a circle. So that's encouraging, and it turned out that all the various theorems we needed infinite cycles for now suddenly worked. The proofs are not easier. They get harder, sometimes a lot harder. But I haven't yet, even to this day, found a reasonable statement about cycles in finite graphs whose version for locally finite graphs in this setup is false. There are many statements that we can't prove, but there's no counterexample. So that just the meta theorem is, that's just the right definition. Now here's a caveat. We can prove these theorems sometimes, but do we know what circles look like? So what about this mess? Is it no longer a mess? Well, we have a definition, but do we know what these things look like? Well, let me close with one example that is a little intimidating, or it was for me, but I got used to it, and it's just a reminder that it's damn hard or impossible to get your grips on a combinatorial definition of the right infinite cycles, which are those things that are homeomorphic to circles to the unit, to S1 in mod G. So one does need topological arguments, but they're always the same simple topological arguments. And the book has a section in the infinite chapter about how these circles can be in a very standard, neat way obtained as limits, more precisely inverse limits, of finite cycles in certain minors, in certain finite minors of the given graph. So we know exactly how to get them, and in this limit process, one has to practice how that works, and then you can prove theorems using this limit process without knowing what they look like. So here's an example. It's called the wild circle. So let's start with a binary tree. And then from every vertex in the binary tree, we go left, right, and right, left, and make those things adjacent. So no. Can one see this? Yeah, maybe. So for this vertex, we go left, right, and we go right, left, and we add this edge. For this vertex, we go left, right, and right, left, and we add this edge. And similarly for that, and we keep doing that. From every newly added edge, we take the left vertex and we follow the ray going right, 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 and we take the right vertex and follow the ray going left, left, left. Right, I forgot that, sorry. So here as well, from the left vertex we go right, 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 from the right vertex we go left, 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 and notice that there are no edges here, right? So right, and now this bottom double ray together with all these yellow double rays, now these do form a circle. And that's the wild circle, for obvious reasons. It uses all the ends. So this has continue many ends lying on this one circle. That takes a bit of proof. So these yellow rays aren't, there are only countably many of those, right? But there are uncountably many, continue many ends, but all these ends that come from the sort of wiggly rays in the tree they also define ends, and these ends are also elements of that circle. So the union of these double rays plus all the ends is homeomorphic to S1. That does take a little bit of proof. And notice, for example, that, I mean, this yellow ray here, that goes to some end. That end lies in the circle. This end here is an end of this double ray, and that comes from the left. I should, yeah. So if I draw it above here, then this double ray comes from the left. So this ray approaches this point from the left. And from the right, there is no yellow ray that converges to this end, or that is an element of that end. So these, they are like this. Right. So between any two, there is another. Between any two of these double rays, of these yellow double rays, there lies another double ray. It's much like the rationals in the unit interval. Between any two rationals, you find another rational, although there are only countably many. And they have the same order structure. These double rays have the same order structure. Between any two of them, there's another. Incidentally, having talked about universal graphs, there's an exercise asking you to prove that the rationals are universal in the set of linear orderings, the countable linear orderings. So they contain every countable linearly ordered set. And the proof is and there's only one of these. So the proof is exactly like what we did for graphs, this back and forth thing. Right, so that's just an aside. So here, the order type of these double rays, if you think of them as lying between left and right, is the same as the order type of the rationals going from 0 to 1. Yeah, so that's the wild circle, and it is one of these things that appears as in these theorems, but we never have to look at it. We can prove things about it without saying, oh, where exactly does this go? We don't know. It doesn't matter. So this gets sort of somewhat exciting, and that, I think, is all I want to say. Any questions? Other than when is the next course on infinite graphs? Okay, thank you very much.